This program is brought to you by Stanford University. Please visit us at stanford.edu.
Tonight I want to, thank you. I want to begin studying how things change with time in quantum mechanics. We started a little bit, but let me just very quickly remind you, very quickly again, how they change in time in classical physics. We've discussed over and over how they change in time for a discrete system like a coin toss, up, down, up, down, up, down, or heads, tails, heads, tails, heads, tails, that sort of thing. Always you have to postulate a law of change, a law of evolution, and that corresponds to a set of arrows which tell you where to move next and so forth. Notice that if a system is discrete, if it only has a finite number of states or a finite number of independent states, then classically the only meaning you can make of its evolution would have to be with discrete time intervals, where you would sample the system only in discrete intervals because there's no continuous way to go from one to another. Heads, tails, heads, tails. Okay. Well, certainly classical physics allows continuous time, but in order to have it, we have to go to the Hamiltonian quantum mechanics, or the classical mechanics of continuous systems. Continuous systems means, for example, particles which can be anywheres on an axis, so that the position is continuous, the momentum is continuous, and so forth. But still, the classical rules of evolution are predictive, and instead of being hops from one discrete state to another, they become flows in phase space. Now, if you took my class in classical mechanics, you'll remember what I'm saying. If you didn't and you don't know what I'm saying, it's not going to be terribly important, but I did want to connect with classical mechanics a little bit. If we have, for example, a particle on a line is characterized by a position x and either a velocity or, better yet, a momentum p, and so that at every instant of time it has a position and a momentum, something that we know is not going to be right in quantum mechanics. But we can describe the evolution in terms of a flow on, this is called phase space, a flow on the phase space, which is simply another way of saying that if you start the system at any point, a position and a velocity or a momentum, it will move in general, and it will move along one of these flow lines. The flow lines are described by a Hamiltonian. Now, I just want to very briefly review classical mechanics, extremely briefly. The law of evolution of a classical mechanical system is through the object that's called the Hamiltonian. And the Hamiltonian is a function of positions and momenta, x's and p's. However many x's and p's there are, there's a p for every x and an x for every p. If there are 7 coordinates, 7 particles, and there's 7 times 3 coordinates, 7 times 3 momenta, but let's just write it as 1 coordinate, 1 momenta. All right, that Hamiltonian determines, it is the energy of the system as a function of positions and momenta. As a function of positions, typically it would give you the potential energy. As a function of momenta, it would give you the kinetic energy. So a simple example, for example, would be p squared over 2m for the kinetic energy, plus some potential energy as a function of position. That would be an example. The systems have Hamiltonians. The Hamiltonians represent the energy, but they're written in terms of positions and momenta. But the law of evolution, which is a deterministic law of evolution, is a law which tells you wherever you start, it tells you where you'll be after a very brief interval. So it's just described, instead of a bunch of points with arrows connecting them in some way, it becomes a set of flow lines which tells you wherever you begin, where you go next. All right, the equations. The mathematical equations are differential equations. The differential equations, which are written in terms of the Hamiltonian. I'm just going to write them down for you, Hamilton's equations. Hamilton's equations are that the derivative of the Hamiltonian with respect to momentum, let's just do it here. Derivative of the Hamiltonian with respect to momentum in this case would just be P over M. P over M is velocity. Momentum is mass times velocity. So P over M is just velocity, and velocity is just the time derivative of x. That's x dot. And the other equation is basically F equals ma, the derivative of the Hamiltonian with respect to position gives you minus the force. That's the derivative of the potential energy with respect to position is minus the force, and that's the time rate of change, or minus the time rate of change of the momentum. Those are Hamilton's equations. Now, supposing you have some function, let's call it f, an observable function of position and momentum. I call it an observable because I mean that, that you can make a measurement of it, p and x, the x squared plus p squared, or whatever it happens to be, and I want to compute its time derivative. All right? Its time derivative is given by the derivative of f with respect to p times the time derivative of p plus the derivative of f with respect to x times the time derivative of x. But we have a formula for p dot. Let's go first to x dot. We have a formula for x dot. It's dh by dp. So we can write over here dh by dp and likewise over here for p dot, oh boy. I'm taking some of this home if you all right, and p dot is dh by dx. This combination, given two functions h and f, one of them happens to be the Hamiltonian here, one of them happens to be some arbitrary observable, but given two functions of x and p, this combination is called the Poisson bracket. You don't have to remember it. I just want you to remember that the time evolution of things, of anything, is gotten by some operation that involves the Hamiltonian. This is called the Poisson bracket of h. This is the Poisson bracket of f with h, and we would write this, the Poisson bracket of h, of f with h. And the definition of the Poisson bracket of two objects is just this particular combination, where is it? The df by dx, dh by dp, and so forth. You can read it yourself, given any two things. This is the basic structure of classical mechanics. The Hamiltonian determines a flow. It tells you how x and p change with time, so it determines a flow. And if I have any interesting quantity, I can determine how it changes with time along the flow. I can tell you how it changes with time along the flow by Poisson brackets. Now, it's not terribly important to know very much about Poisson brackets. The main point is the Hamiltonian is the generator of time evolution. Those are the words. The Hamiltonian generates the time evolution of a system. The same is true in quantum mechanics, and it's much more intuitive. This, to me, was always very obscure. I mean, I learned it, I understood it, I knew how to use it. I even knew where it came from, but it always seemed like too complicated an expression here. I always thought it was just something simpler must underlie it. And something simpler does underlie it. What underlies it is quantum mechanics. Quantum mechanics is, in many respects, simpler and in many ways mathematically easier to understand. All right, so how do systems evolve with time? What's the basic rule for the evolution of a system? The basic rule is that relationships between states don't change with time. Let's suppose that some initial state of a system evolves. Let the arrow stand for evolves over a period of time. We could put a T here for indicating a period of time. Evolves over a period of time to something that I'll call U times A. And of course, U I intend to mean a unitary operator. Unitary, we discussed last time what it meant. Let me just remind you what unitary means. It means that it times its Hermitian conjugate is the unit operator, or that its Hermitian conjugate is its inverse. That's the definition of a unitary operator. All right, so let's suppose that state A evolves under time evolution to U times A. And of course, we should indicate here this U should be parameterized with how much time evolved. T is the amount of time which evolved, some operation or some operator which acts on the state, initial state, to give the state after time t. So here it is after time t. Let's suppose the same thing is true, that if we started with state B after the same evolution, of course we would just write the same thing. Not quite the same thing. We would write the action of, we can call this the evolution operator. Let's give it a name. The evolution operator acts on A to give whatever A becomes. It acts on B to give whatever B becomes. All right, now let me write this second equation in terms of bra vectors. In terms of bra vectors, it becomes B evolves. Now we have to complex conjugate. B is the conjugate or the bra vector. In order to conjugate, we must do something with this U, namely we have to replace it by its Hermitian conjugate. If you like, bra vectors are sort of complex conjugates of ket vectors, and Hermitian conjugates of operators are complex conjugates of the original operator. So this is the operation of conjugation. All right, well, what happens now to the inner product of A with B? We started with two possible states which had some relationship between them. The relationship simply is codified by the inner product between them, B with A. If B is orthogonal to A, they're surely different. If B is parallel to A, they're the same state. And if B and A overlap, then anything which is certain in B has a certain probability of occurring if you're in the state vector A, and vice versa. So this is the basic relationship, mathematical relationship between states, what the inner product between them is. Let's see what happens to it after a period of time. After a period of time, this goes to, let's have it come out over here. After a period of time, it goes to, now what happens to B? B becomes U dagger times B. That's what happens to B. And A becomes U times A. If we insist that the relationships between vectors are preserved with time, if you want to picture this in your head, think of these vectors as evolving in time. The state vectors evolve in time, but keeping the angles between them fixed. In other words, the whole space of states sort of rotates. That's the way you can think about it, with all vectors and relationships between vectors being kept fixed. In that case, that tells you that BA must equal B U dagger UA for all A and B. The implication, the mathematical implication of that is that U is unitary, that U dagger times U is just the unit operator. All right, so that's the fundamental underlying principle of time evolution of state vectors in quantum mechanics. It's the governing principle that things which are orthogonal stay orthogonal. That's really it. In fact, that's enough to ensure all of this. So states which are orthogonal stay orthogonal. Things which are fundamentally dissimilar, so dissimilar that you can tell the difference between them in a single experiment, stay that way. Good. All right, now let's study this object u of t. Let's write a more general equation. Let's write an equation in the following way. Let's suppose we start at time t, and we have, at time t, we have a system with a state vector psi of t. It could be a particle on a line. It could be our friend the photon polarization, but it's a state vector at time t. T eventually becomes t plus t, capital T. The system has evolved through an amount of time, capital T. So it follows, it's just a special application of what I've written up there, that psi of t evolves to, oh, let me write it this way. Yeah, let me write it a special way. After a time, capital T, the system has evolved to psi of t plus capital T. New time is t plus capital T, amount of time capital T is evolved, and that, according to what we've written up there, must just be u of capital T times psi of small t. All this says is if we want to push the system ahead by an amount of time capital T, we do it by applying the evolution operator u of capital T. So that's the first fact. That's the first thing. Time evolution through a certain amount of time is governed by a unitary operator. Next, let's see what we can learn about this. What happens if capital T is 0? If capital T is 0, that's no evolution at all. If there's no evolution at all, then u must be the unit operator. In other words, if capital T was 0, then psi of t plus capital T had better just be psi of the original t. The implication of that is u of 0, no evolution at all, is just a unit, the identity operator. It does nothing. It leaves the state unchanged. Okay? All right, so that's the first fact. Now, supposing one way of finding out how systems evolve is to let them evolve through very, very short time intervals. If we want to get from time t to time t plus delta t, or time t plus capital T, we can break up that capital T into a lot of little time intervals and evolve it over one small time interval, then another small time interval, then another small time interval. So an interesting question then is, what is u of a very small time interval? If we know what u is for a very small time interval, we can compound it together and find out how a system evolves over a finite time interval. So let's say u of epsilon. Epsilon here means a very small time. Technically, it's a small enough time that I can ignore things quadratic in epsilon. I can work the first order in epsilon, and that's what I'm going to do. The first order in epsilon, what can I say about u of epsilon when epsilon is small? Well, the 0th order, in other words, when epsilon is 0, we should just write down 1. And then there's a small correction to that 1. If epsilon is small, the correction is small. So let's write down epsilon times something. Something which has, we could just call it L or S for something. I'm going to write it in a very peculiar way, but the reason for it will become obvious later. This is entirely a convention. This is entirely a convention, but I'm going to write it as, I think, minus. Do I want a minus sign? Yes, I want a minus sign, an I, an epsilon. That's the important thing, is the epsilon. And I'm going to write H divided by Planck's constant. Now, there's no content to all of this I and H bar here. It can all be absorbed into the definition of capital H. I've written it that way because later on we're going to find out that capital H has a significance as the energy of the system, or the quantum analog of the Hamiltonian. But for the moment, this is just an arbitrary convention that I put an I there. We'll see in a moment why the I is there. the fact that Planck's constant is in the denominator, that's purely definition of capital H. There's no content in it yet. It's just putting the small quantity that goes into quantum mechanics, it's putting it into the formula in order that later on we will recognize this thing as a certain classical object. All right, let's see what we can learn about capital H here. We have to have that U of epsilon, or U dagger of epsilon, times U of epsilon to first order in epsilon. We're keeping things to first order in epsilon and only to first order. That should be equal to 1. Let's write it out. What is U dagger? Well, let's write down U dagger over here. U dagger is equal to 1 plus I epsilon over H bar times the Hermitian conjugate of H. When you Hermitian conjugate something, you have to change all the coefficients. You have to complex conjugate all the coefficients. I epsilon becomes minus I epsilon, minus I epsilon becomes I epsilon. And when you Hermitian conjugate, you have to Hermitian conjugate the operators. All right, so this is the formula for U dagger. So let's write it out. 1 plus I epsilon over H bar H times 1 minus I epsilon over H bar times H has to be equal to 1. 1 meaning the unit operator. And of course, 1 here also means the unit operator. This is an operator equation. H dagger. Which one? This one, I think. H dagger here. All right, we multiply it out. 1 times 1 is 1. That's going to cancel this 1. Anything of order epsilon squared is too small to worry about to the first order. And the only thing that we have will be an I epsilon over H bar. And then from here times 1, we'll have H dagger. But from 1 times here, we will have minus H. 1 times the minus H, and then the H dagger times the 1. Those are the two terms that appear here. Oh, we left out the 1. 1 times 1 is 1, but that cancels the 1 here. So the result is the condition that U be unitary is the condition that H dagger equals H, or H dagger minus H equals 0. Same thing as saying H dagger equals H. In other words, whatever H is, it has to equal its own Hermitian conjugate. That, of course, is the condition that H is Hermitian. So what we learn from this basic principle that relationships have to be invariant under time evolution, relationships of vectors, is we learn that for a small interval of time, the evolution proceeds by some kind of Hermitian operator. H dagger equals H. It doesn't tell us what H is. But it does tell us whatever H is, it should be Hermitian. Now, Hermitian in quantum mechanics means the object is an observable. What are the implications of it being observable? First of all, that it has an orthonormal basis of eigenstates. All of its eigenvalues are real. And it's something which can be measured in the laboratory. That's what it means to be observable. The postulate of quantum mechanics is that all Hermitian operators correspond to things that can be observed, or physically interesting quantities. They may be very hard to actually measure, but in principle, they should be measurable. And so whatever H is, it's some physical quantity. The interpretation of it, now we can give it a name. It corresponds, its eigenvalues are the things that you measure when you measure H. Its eigenvalues have a name. They are called energy. We can't see yet at this point that they correspond to the same quantities that we define in classical physics. We will have to do some more. We cannot see that, no more than we could see that the momentum, the strange definition of the momentum that we had, what was it? Minus I h bar d by dx, that operator we identified with momentum. I told you sometime later we will check that this object behaves like the classical momentum of a particle when a wave packet moves. In the same sense, we will eventually check, I don't think we'll do it tonight, but we'll eventually check in not too long a time, that h, or its average value, the expectation value of h, the average of h, evolves or behaves exactly the same way, has the same value as the classical energy of a system, or approximately the same value. But not for now. For now, we're just going to call the eigenvalues the energy, and we're going to call this object the Hamiltonian. So, we've learned a new principle that there's a Hermitian operator called the Hamiltonian, which governs the evolution of a system as it evolves in time. Are there any questions up till now? Now, if we know how a system evolves for a short period of time, that presumably means we can write some differential equation governing how the system evolves with time. So let's think about that.
So a question.
Yeah.
In the classical limit where h bar goes to 0, you got to divide by 0 in the denominator. Is that
Well, that's
it's too early to take classical limits?
the classical limit is simply the limit in which the energy of the system is very large in units of h bar. Actually, it's not energy, it's energy times time, but epsilon has units of a time. So epsilon times h has units of h bar. But the classical limit is simply the limit in which this quantity over h bar is much, much bigger than 1. So
It's not necessarily goes to 0, it just gets very small.
yeah. We have to ask at the end, what's left over? What things have good limits in the limit that h bar goes to 0? I've written it in a form here where in the classical limit, when everything is kept classical, h has a good limit. All right, but we can't see that now. For now, that h bar is just an arbitrary thing that I threw into the formula. About as arbitrary as this h bar which appears in here. In fact, it's very similar h bar. Okay, let's ask now if we can write a differential equation for how the state of a system changes with time. Let's think about that. Here's what we can write. We can write psi of t plus epsilon, small change in time from t to t plus epsilon, must equal, now on the one hand it has to equal this u of epsilon times psi, but let's not write that. Let's just write that it's 1 minus I epsilon h over h bar. Within about 5 minutes from now, I'm going to set h bar equal to 1. I wanted to put it in once and for all so you see where it goes, but for the time being, let's leave it. Eventually, I'll probably set it equal to 1. It's just a nuisance to write. It's this times psi of t. Okay, so to move ahead, to push ahead a little bit in time, you apply u. You apply u. But u is 1 minus I epsilon h over h bar. Okay, let's manipulate the equation a little bit. First of all, the 1 times psi just gives psi, and we can transpose it over to the left-hand side. So we can write this as psi of t plus epsilon minus psi of t. That's taking care of this, and it's taking care of the 1 here. That is equal to minus I epsilon h over h bar times psi itself. Now let's divide by epsilon. Dividing by epsilon gives us a left-hand side, which is obviously a derivative of psi. It's the derivative of psi with respect to time. I'm simply using the formula that a derivative is the difference divided by the small change in the argument of the function, in the limit that the small change goes to 0. This is just the derivative. I'll write it as a partial derivative, just to indicate that I'm only changing time, nothing else in the problem. The derivative of psi with respect to time is equal to minus I h over h bar times psi. This is telling us how the state changes if we know the Hamiltonian. If we know the action of the Hamiltonian on every state, then we can predict what it's going to be in the next instant of time. If we can predict what it's going to be in the next instant of time, we can do next instant, next instant, next instant, and build up the entire evolution of the system. This is simply a differential equation which tells us how psi changes if we know h. This equation has a name. Anybody know the name of it? That's the Schrodinger equation. That's the Schrodinger equation. It's the abstract general form of the Schrodinger equation. It's not the equation Schrodinger wrote down. To my knowledge, I think the first one to write it in this form was Dirac. Let's multiply it. Let's multiply it by h, by little h bar, and by I. So if I multiply it by I, there's I h bar on the left. I times minus I is plus 1. So I can also write it this way. I h bar d psi by dt is the Hamiltonian operator times psi. That's sort of very similar to this formula. This said that a derivative with respect to position is related to the momentum. This says the derivative with respect to time is related in a similar way to the energy, to the Hamiltonian. Notice there's a difference in sign. This is purely a convention, that there's a minus sign here and a plus sign here. Can everybody see the plus sign? It's in the corner of the, it's plus here. I'm going to move it over a little bit. I h bar. All right, that's the basic idea of the Schrodinger equation, how systems evolve with time. There's another equation we can write. Now this equation is practically definition, not much more. Let's put it up here. Yeah, let's leave it for a moment. We'll come back to it. I was going to write the eigenvalue equation for h, but I'm not going to do it now. All right. Let's think about a couple of examples and what this says, how it was actually used to predict the future, so to speak, to predict the future from the present and to see how it affects measurements of things. Let's go back to our simple system of polarization of photons. Okay? And let me suppose I have some sort of material that I've constructed which shifts the energy of a photon of a given wavelength depending on the polarization. You know, I don't have to tell you, that a photon of a given wavelength has a certain energy. Okay? Energy is related to wavelength. But that relationship can change when the photon moves through a material. Right? So given the wavelength, you might construct a photon of a given wavelength in a material. It has a certain energy, but that energy might be different than it would be outside the material. That's straightforward. There's nothing spectacular about that. But I might have a material which has a certain polarization to it, so that the two states of polarization might actually have different energy from each other. That's quite conceivable. So let's suppose that the X and Y polarizations actually have different energy, and we'll say that the X polarization has energy E1 and the Y polarization has energy E2, just to give them names. So we've created a material in which a photon of some particular wavelength has energy E1 or E2, depending on which polarization it has. That can be translated into a statement about the Hamiltonian. It says that the Hamiltonian is an operator that has two eigenvalues, E1 and E2, and that the two states of polarization are eigenvectors of that Hamiltonian. So let's write it down. It says that H on, I'll tell you what, I'm going to call this one X and this one Y, as we did before. On X is equal to E1 on X. X does not stand for the position now, it just stands for the polarization. We're forgetting entirely the position of the photon. And H on Y is equal to E2 on Y. All right, so the two states of polarization are being assumed. I'm making an assumption now. I'm making an assumption that whatever the Hamiltonian is, that the X component, the X polarization and the Y polarization are both eigenvectors with eigenvalue E1 and E2. Okay, that's the material that I've constructed. This particular photon of this particular wavelength, the two polarizations have different energy. What does that imply about the evolution of this photon as it moves through the material? Does it have any interesting experimental consequences? And we'll see that it does. Quite interesting. Let's begin. Okay, so let's start with some initial state of the photon polarization. Let's call it, well, yeah. It's psi of t. Here's the state vector of the photon polarization at time t. There's only two states of polarization, and we usually write the X component as the upper component of a column vector, and the lower component of a column vector is the Y component. So let's just write that psi of t can be identified with the column vector alpha of t and beta of t. Alpha of t is the amplitude that the photon has X polarization. Beta is the amplitude that the photon has Y polarization. The probability as a function of time that the photon has X polarization would be alpha star alpha, and likewise for beta star beta, that would be the polarization probability to be Y. Okay, everybody remember this? If not, tell me now and I'll ignore you. All right, so that's psi of t. And let's write down now the Schrodinger equation explicitly. Where is it? We've erased it off the blackboard. I hope not. No, there it is. Let's write down the Schrodinger equation explicitly and solve it. I can think of no better way of illustrating what it means than to explicitly write it down and solve it for this very simple system. All right? So we begin with I h bar. Let me throw away h bar now. H bar equals 1 from now on, except when I want to illustrate some point about h bar itself. H bar is equal to 1 from now on. Okay, so let's write this equation. d psi by dt, what does that mean? That means the time derivative of this column vector here. The time derivative of the column vector is just another column vector whose entries are the time derivatives. All right, so d psi by dt can just be identified with the column vector. Let's call it alpha dot of t and beta dot of t. Dot indicates time derivative as usual. That's d psi by dt. Let's multiply it by I, not by h bar. H bar was set equal to 1, so let's multiply it by I. And what does that equal? That equals the Hamiltonian acting on psi. First of all, let's write out the matrix that's identified with the Hamiltonian. The matrix that's identified with the Hamiltonian is just very simple. It's just E2, 0, 0, E1. It has eigenvectors x and y with oh, that's wrong. E1 and E2. E1 and E2. E1 and E2. The two eigenvectors, the two eigenvalues are E1 and E2, and the two eigenvectors are just x and y, and here it's displayed in the form of a matrix. Okay, so let's write down now that this is equal to h times psi. H is E1, 0, 0, E2 on psi, and psi is just alpha beta. Okay, what is this equal to? The right-hand side, we can multiply out the matrix times the column vector, and it's just E1 alpha E2 beta. This is now two differential equations, one for the upper component and one for the lower component. Whenever you get an equation like this, you can read it as several different equations, one for each component. Let's take the upper component. The upper component equation now just becomes a perfectly ordinary equation, I times the alpha by dt is equal to E1 alpha. That doesn't look so hard to solve. And the lower equation is very similar. I times d beta by dt is equal to E2 times beta. I think maybe it would be a little easier and more recognizable if I would multiply by minus I. Then it would get rid of the I over here and put a minus I over here. And we get rid of the I over here and put a minus I over here. So both equations, they're two, in fact, for the simple example, the alphas and the betas aren't even coupled together. They satisfy separate equations with not even any mixing between them. Very simple equations. And the solutions are simple. What's the solution of an equation where the derivative of an object is proportional to the object itself with a coefficient? Exponential. Right? So the solution of the first equation here is that alpha is equal to whatever it is at time 0, alpha of 0. In fact, let's call this alpha of t is equal to alpha of time 0 times e to the minus I E1 t. If I differentiate this with respect to time, it just pulls down a minus I E1, which is exactly what's here. Okay. And let me simplify the notation by just calling alpha at time 0. Let me just call it alpha. There's too many brackets and other little pieces of nuisance to write down. So we'll just call alpha is alpha at time t equals 0. And as time goes on, it just gets multiplied by e to the I et. What about beta of t? Similar thing. That's equal to beta times e to the minus I e2 t. And so the state of the system is represented by a column vector. We can write the column vector now as a function of time, alpha e to the minus I e1t, and beta e to the minus I e2t. Now let me just point out at this point where h bar would have gone had I included it. H bar would go in the denominator under the e's. It would go in the exponent, but as a denominator, E1 over h bar if I had included it. All right. All right, so we see what the energies correspond to. They correspond to phases, to oscillations in the entries here, but different oscillations for the two entries. Different oscillations, one with E1 and one with E2. That's the state of the system after a time t. Now let's ask, what if we did some measurements? Supposing we measured the polarization of the photon. In particular, we measure the photon polarization in the xy plane, the x versus y polarization. We run it through an x polarizer. We run the photon through an x polarizer, and we find the probability that it's polarized along the x-axis. All right. What's the answer to that? It's just the entry up here, the square of the entry in the top. This one corresponds to x, this one corresponds to y. The probability that the polarization, let's call it probability, that the polarization is +1, but there's too many indices here. The probability that the x polarization is plus, in other words, that it's polarized along the x-axis, that the photon goes through the polarizer, that's just going to be alpha e to the minus I omega, e to the minus I E1t times its own complex conjugate. Remember, we take these entries and we multiply them by their own complex conjugate. And what's that going to give? That's just going to give alpha star alpha. The e to the I et is not going to do anything when we multiply it by its own complex conjugate. So nothing's happened. I mean, this whole business about the time evolution hasn't done anything. It hasn't changed the probability for x polarization, not even a little bit. It's done nothing to the probability of x polarization. Likewise, the probability that it's polarized along the y-axis is just beta star beta. So at first sight, it seems like this time evolution hasn't led to any big deal. It's done nothing. It's just multiplied the individual components there by phases, but that hasn't changed any probability. The interesting thing happens when we decide to use a different polarizer. So let's imagine now that we took a different polarizer. We run it through after having we take this state, here it is, and we run it through not a vertical horizontal polarizer, not an X polarizer, but we run it through a polarizer that's, for example, polarized along the 45-degree axis. And ask, what's the probability that the photon goes through the polarizer at 45 degrees? All right, so let's do that little calculation. All right, first of all, the state vector corresponding to polarization along 45 degrees, what is that? That corresponds to the column vector 1 over square root of 2, 1 over square root of 2. What do we have to do? We have to take psi, the original psi, or not the original psi, but psi as it is over here, and take its inner product with the polarization state polarized at 45 degrees, and take the square of that. We'll take the square soon enough. This is called the amplitude that if we measure the diagonal polarization, what did we call this? We had a name for this, the slash polarization, that if we measure the slash polarization, we'll either go through or it won't go through. This is the thing that gets squared. Let's not square it yet. This is equal to, okay, we take the row vector, the bra vector is slash, and that's just 1 over square root of 2, 1 over square root of 2. On the other hand, after a time t, we have alpha e to the minus I E1t, beta e to the minus I E2t, and we have to take the inner product of those. This is very simple. It's just equal to 1 over square root of 2 alpha e to the minus I E1t plus beta over square root of 2 e to the minus I E2t. That's the amplitude. Okay. Now what do we have to do with it in order to get a probability? To get a probability, we have to multiply it by its own complex conjugate. We have to square it. Here's what's going to happen. Here's the point. When we square a thing like this, there are two kinds of terms. There are the terms coming from squaring the individual components, and there are the cross terms. Let's look at the individual components. The individual components will be alpha star alpha over 2, and the e to the I ETs will cancel. When we multiply this by its own complex conjugate, the e to the I et will cancel. Likewise, when we multiply this by its own complex conjugate, it's the cross term. It's the term gotten from multiplying this by this, which is going to have an interesting time dependence. All right, so let's examine that. Let's actually examine it and see what we get. But before we do, I want to simplify the problem a little bit by choosing alpha and beta in a simple way. What I'm going to do is I'm going to assume that alpha and beta are equal and both equal to 1 over square root of 2. This corresponds to the following experiment. We send the photon through a polarizer polarized along 45 degrees. That gives us an initial state at time t equals 0, which is just polarized at 45 degrees. Then it goes downstream in this strange material where the vertical polarization states have different energy. All right, so the two vertical polarizations have different energy, and then we send it through a second polarizer oriented in exactly the same direction. Ordinarily, we would fully expect that it would go right through, and with probability 1, pass through the second polarizer. Let's see if that's true. The initial state that the photon comes out of the polarizer with is just, this is just what? It's, let's call that time t equals 0. That just corresponds to alpha and beta with no time dependence. But let's set alpha and beta themselves equal to 1 over square root of 2. So in passing through this polarizer, the photon comes out at the other side with alpha equals 1 over square root of 2 and beta equals 1 over square root of 2. It's just a special case of this, where alpha and beta happen to be both themselves 1 over square root of 2. That's how the photon comes out. Then the photon propagates for a certain time t until it gets to the other polarizer. Right? That's what we have here. We can now write this. We can specialize it to the case 1 over square root of 2, 1 over square root of 2. So here's how the photon came out. It propagated downstream for a time t, and then we want to know what's the probability that it passes through the second polarizer, polarized exactly the same way as the first polarizer. So this becomes 1/2 here, and this also becomes 1/2. I'm just doing this to put some numbers in, to see what comes out. All right, so this is now the amplitude that the photon passes through the second polarizer. Let's calculate the probability. The probability is simply this times its own complex conjugate.
Isn't that 1 over the square root of 2 times?
No, there were 2 square roots of 2 here.
Oh, okay. That's
Yeah, right. Okay, so let's see what comes out. We're going to have 1/2 times 1/2 when I square this. Let's pull out the factor of 1/2 and square it. And then we're going to have e to the I minus I e1t plus e to the minus I e2t, all times e to the plus I e1t plus e to the plus I e2t. This bracket is simply the complex conjugate of this bracket. So the 1/2 times 1/2, that's just squaring the overall factor of 1/2 here, and then I've multiplied this by its own complex conjugate. The whole thing is then 1/4, and let's see what we get. E to the minus I et e1t times e to the I e1t, that's 1. This one times this one is 1. All right, we're finished with that. Let's mark off as we do them. We've taken care of this product. Now let's take care of this product. That's 1 again. So that's plus 2. Now we have 2 cross terms. And the 2 cross terms are, let's see what they are. They're e to the minus I e1t times e to the plus I e2t. So that's e to the I E2 minus E1 t. And the other term is simply the complex conjugate of this, plus e to the I, e2, well, let's write it there, e to the minus I, e2 minus e1 t. I think it's a little bit helpful to define E2 minus E1. What is E2 minus E1? It's the difference of energy of the two polarization states. Notice that the answer only depends on the energy difference of the two polarization states. This is deep, important. Physics only depends on energy differences. Nothing would change if you added a constant to the energy of a system. All right, so it only depends, as we might have guessed in the first place, it only depends on the energy differences. Let's call the energy difference E2 minus E1. Let's call it delta E, just so I can stop writing E1s and E2s. Let's call it delta E, the difference of the energy of the X polarization and the Y polarization. Okay, what is e to the I something plus e to the minus I times that same thing? E to the ix plus e to the minus ix. It's just twice the cosine. So this whole thing is just, I can now erase all the exponentials, and it just becomes twice the cosine of delta E times t. Let's write that out. Twice the cosine plus twice the cosine of delta E times t. Okay, let's review what we did. We have a material which gives different energies to the vertical and horizontal polarizations. We then sent through the material, we sent through a polarizer, a photon, to polarize it along the 45-degree axis. And then we waited a while, we went downstream a ways, and after a time t, the photon is sent through a second polarizer, oriented exactly the same direction as the first one, and we ask what's the probability that it goes through. Here it is, and notice that it oscillates as a function of time. It oscillates with a frequency which is determined by the energy difference. If we were to plot this function, if we plotted the function, well, what is it? It's 1/2, the quarters mixed with this is 1/2 plus 1/2 cosine delta Et. It's a function at time t equals 0, 1/2 plus 1/2 is 1. Now what's the meaning of that? Time t equals 0 would correspond to putting the second polarizer close enough to the first polarizer that nothing much happens, no time evolution between them. If the time evolution between them is no time at all, then the photon surely goes through the second polarizer. There's been no time for the state to change, and so if it goes through two parallel polarizers, the probability to get through the second one is 1. That's 1 plus 1, 1/2 plus 1/2. But then some time evolves, and after a time delta E times whatever it is, the probability has actually gone to 0 that it gets through the second polarizer. It looks like this. Doesn't get negative, never gets negative. Probabilities can't get negative. It just oscillates, going from 1 to 0 to 1 to 0 to 1 to 0. Of course, when it goes to 0, that's an indication that it will definitely pass through the polarizer at 90 degrees. So the polarization of the photon, after a certain time, has rotated. It's basically rotated. If we wait enough time until we come to the 0 over here, then it's certain that it will pass through this polarizer. So the polarization has rotated. It's not a circularly polarized photon, but the linear polarization has rotated, and it just keeps rotating as you go downstream. So this funny material, which splits the energy of the two photons, has the effect, has a real physical effect. It has the real physical effect of causing the polarization to rotate as you go downstream. That, of course, is observable. So this is kind of interesting. If we measure not the horizontal vertical polarization, there's no effect on that. There was no effect on the probabilities for the horizontal and vertical polarization, but we find an interesting effect on the probabilities for the slashed polarizations. That's the basic phenomenon, and this is an interference phenomenon. This is interference of probability amplitudes causing these oscillations. Destructive interference over here, constructive interference over here. And this is all with a single photon. All right, any questions about up till now?
This material has to be completely filling the space.
Yeah, let's assume the material is filling the space between the polarizers. And it goes on and on forever in every direction.
But, yeah.
Don't ask me how to make the material. I haven't thought about it very hard. I'm sure if we went into the laboratory and asked the technician... What's that?
Call it magic material.
Magic material. If we went in and asked the technician in the lab here, he'd probably pull out a piece of something, and it's probably got some name, but I don't know what it is. Yeah, question?
Yeah, so the question is, so you're plotting time on that sort of x-axis.
Yeah, time on the x-axis.
So that means that after a certain amount of time, the probability of going through the material in that state of polarization goes to 0.
Well, let's just use some precise language. The probability that it passes through the other polarizer in the same direction has gone to 0. That's the thing to say.
Okay. So depending on when you look at it.
Well, or how far downstream you put the other polarizer. Remember, the photon moves with a certain velocity, and so the velocity determines how much time it, for our simple purposes here, we can just identify the distance downstream with the time in some appropriate way. Yeah. Since we're not very much worried about the actual motion of the photon, only the motion of its polarization. So isolating out the polarization, we can then identify the time downstream with the velocity of the photon, which may or may not be the speed of light in this strange material. Well, it is the speed of light in the strange material, excuse me.
What effect would it have on a circularly polarized photon?
Oh, that's an interesting question. I don't know. I'm not sure. I suspect it would cause, I would suspect it would cause an oscillation back and forth between the between the two circular polarizations. But this is something you can do, all right? All we have to do is put an eye down here. Okay, so let's do it. It will just put an eye over here. It'll put an eye over here. So there will be an eye over here and a minus eye over here. What will that do? Oh, it looks like it will change. Yeah, it looks like it'll turn this into sine, but it will leave the oscillation. Yeah. Thank you. That was good. Yes.
It's something a little bit unsettling to me.
That's a little loud.
You arbitrarily choosing, x and y this way or x and y this way, and yet it seems to change everything.
Well, we have a material which was constructed in a certain factory, and we've lined it up. So a certain factory, it has two axes in it. They're really fit. If you looked at it through a microscope, you would discover some axes. And we've simply lined those axes up with the x and y axis.
Oh, I see. And this way it's misaligned. The material itself has.
Yeah. The point is, you get an effect when the material itself is misaligned with the polarizers. It's misaligned with the polarizers. Then you see something interesting happen. You see this rotation of the polarization, or the oscillation between the two states of circular polarization. So the sign here, when you put an eye in here, would also cause an oscillation of the probabilities. It would look the same, except it would start at 0 and go up to a maximum and so forth. It would correspond to an oscillation between two states of circular polarization, probably becoming elliptically polarized in between. Yeah, that's what would happen. You would have a circular polarization, and the circular polarization, I think, in the vertical direction, would become elliptically polarized and then come out afterwards rotating in the opposite direction as you went downstream. But the main point is that that there are these interference phenomena which really do happen just because of these phases. Notice something else. If the two phases were the same, if E1 equaled E2, if they were exactly the same, then this delta E would be 0, and cosine of 0 is just 1, so this would just be 1 plus 1 is 1, and in other words, if the two energies were the same, then it would behave as if there was no material in there at all.
Which is the same thing when we use the X polarizer to measure the X polarization state.
Yeah.
Then you get the cosine 0.
Yeah, yeah, yeah. Good. But if the two energies are the same, you get no effect on anything. No matter what the orientation the polarizers are, it does nothing. Yeah. So adding the same energy to both polarization states does nothing. And that's a very general property of quantum mechanics, that if you add a constant number to the energy of every state, it does nothing. It has no effect whatever on anything interesting that you can measure. So that's why only energy differences are relevant in physics. Okay, now let's do one more thing before we take a break. Well, we're going to take a break and probably go home, but let's do one other thing, one interesting thing here that let's suppose we have some observable. Some observable, I need a letter, K. K for observable. K is an operator. I'll put a little hat on it, but I'll probably forget it after a while. And I'm interested in its expectation value, its average value. Let's take its average value in the state psi. We can just call that the average of K. If we want it to be even a little bit looser, we might just call it K, which of course would be wrong to call it K because it's just the central value, it's just the average value of K. If the probability distribution is nice and peaked, then most of the times we would measure K somewhere near the probability, somewhere near the expectation value, somewhere near the average value. I won't write this. This is too loose for me. All right, so we'll just call it K. How does this change with time? K is some very definite operator. It represents some specific observable. I want to take the same observable and ask how its value changes with time. So it could be the momentum, it could be the position, or it could be one of the observables associated with the polarization. And I want to know how it changes with time. For example, it could correspond to the observable associated with slashed polarization states. We had worked it out. It was some definite operator. We might ask how it changes with time. So I would like to calculate the time derivative of psi k psi. Why does it change? It changes because the psi's change with time. Right? The state vectors of the system change with time. We're going to take a fixed observable, so we're not going to change the observable that we're talking about. It might correspond to some specific polarization state. We're not going to change it, but we're going to ask how it changes because the state of the system changes with time. Right? So I'd like to calculate that. Well, this is just a product. It's a product of psi, basically the complex conjugate of psi over here with the k in the sandwich in between, but the thing inside, the bologna in the sandwich doesn't change with time, only the bread on the outside changes with time. So we have a product to calculate, the derivative, the time derivative of a product. To calculate the time derivative of a product, it's just the sum of two terms. One term having to do with the time derivative of the bra, the other term having to do with the time derivative of the ket. So we can write this out. This is just a straightforward product rule for derivatives. This is equal to, we first time differentiate the ket, and that gives us psi k, and I'm not going to write the psi dt, I'm just going to write psi dot. And then we have another term where the bra vector is differentiated, and that's plus psi dot k psi. Well, where do we get these psi dots from? Apart from the fact that have we erased them off the blackboard? Okay, so let's see. Let me write down the Schrodinger equation. We get them from the Schrodinger equation. So the Schrodinger equation is that I d psi by dt I d psi by dt, which is also called psi dot, let's just call it psi dot, is equal to h psi. Do I have the sign correct? Yes, I do. We can put the I on the other side, minus I. Psi dot is minus I h psi. Right? We'll also need the corresponding equation for the bra vector. Psi dot is equal to plus I bra vector psi times h. Okay, when you act on bra vectors, you act from the right. When you act on ket vectors, you act from the left. This equation here is just a complex conjugate of this equation. I've changed the sign of the I because to complex conjugate I, you have to change its sign. All right, so we have all the material we need. We have psi dot. What is psi dot? Psi dot is minus I h on psi. So let's put a minus I here. And instead of writing psi dot, we can write h times psi. Well, what about this equation over here? This equation here, we use the bra vector version of it, plus I, and we have to put the h next to the psi. So let's put the h next to the psi. And I think it's plus I. Well, we have two terms which look very similar, but the h and the k come in the opposite order. So what we actually have here is minus I times the expectation value of the commutator of k with h. What is the commutator? The commutator of k with h, this is definition, is just kh minus hk. We've done these things before. We've done commutators of position and momentum. We've done commutators of some of the polarization operators. Here's k with h. So we've learned something interesting. We've learned that the time derivative of the expectation value of a quantity is simply minus I times the expectation value of the same object, the commutator of that object, with the Hamiltonian. It's the Hamiltonian which determines how things evolve with time. Let's condense the equation here. Fundamental theorem about how things change in quantum mechanics. This is equal, now I've erased it and I don't remember what it was. Minus I or plus I? Minus I, but now it depends on, let's just write it this way. expectation value of k, the time derivative of it, is minus I times the expectation value of the commutator. Now, is it h of k with k or k with h? K with h? All right, so to find out how a thing changes with time, you commute it with a Hamiltonian. Let me just remind you that in classical mechanics, what you do if you want to find out how a thing changes with time is you take the Poisson bracket with the Hamiltonian. In both cases, it's the Hamiltonian which tells you how things change, how they change with time. In quantum mechanics, it's the commutator. In classical mechanics, it's the Poisson bracket. Now, in fact, Poisson brackets and commutators are very close to each other. They're very closely connected, and we'll talk about that connection. But for now, and this was a very easy derivation. This was very simple. What did we do? Let me just remind you what we did. We time differentiated this by time differentiating the bra vector and adding to it the time derivative of the ket vector. And then we just used the Schrodinger equation for the time derivative of the ket vector and the time derivative of the bra vector. The opposite sign, which appears here because of the complex conjugate, wound up giving us a commutator. So it's two lines basically, to derive the connection between time derivatives and commutators with Hamiltonians. We could, well, we could apply this to the problem of the polarization and see how the expectation value of polarization would change as the photon moved downstream. I'm not going to do that because I don't have it in my notes. All right, let's take a break for a few minutes. So we proved the theorem that said that the time derivative of any expectation value is related to a certain commutator of the Hamiltonian with the quantity in question. An implication of that is that if a quantity k commutes with the Hamiltonian, in other words, if the commutator is 0, then the time derivative of its expectation value is exactly 0. Exactly 0 in any state. In any state, the time derivative of the expectation value will be 0 if the commutator of k with h is equal to 0. So that's the condition for a conserved quantity. You can prove a stronger theorem. I won't do it tonight. This is simply a theorem about the expectation value of k. I'd like to prove a somewhat stronger theorem. The stronger theorem might say that the probability distribution or the probability for a given value of k doesn't change with time. It's also true. But for the time being, I'll simplify the theorem. The expectation value doesn't change if the object commutes with the Hamiltonian. And that, at least at the level of expectation values, is a statement that any quantity which commutes with the Hamiltonian is conserved. Right? Certainly, the implication goes the other way. If a quantity is conserved, it must, then its expectation value is time independent, definitely. And in that case, it must commute with the Hamiltonian. The implication goes in both directions. If a quantity is conserved, it commutes with a Hamiltonian. If a quantity commutes with a Hamiltonian, then it's conserved. But one special case is the Hamiltonian itself. Any operator commutes with itself. Any operator commutes with itself. A times A is equal to A times A, and it doesn't matter which way you put the A's in. So it implies that the Hamiltonian itself is conserved. The Hamiltonian is some kind of conserved quantity. Let me just point out the classical analog. The classical analog is that the Poisson bracket of any quantity with itself is also 0. What would that be? Let's take some object A. A with B, that's the A by dx, the B by dq, by dp, minus the A by dp, dB by dx. That's the Poisson bracket of A with B. If A and B are equal, then obviously this is equal to 0. The A by dx is the same as dB by dx, and dB by dp is the same as the A by dp, so that this is equal to 0. Again, in classical physics, it follows that any quantity whose Poisson bracket with the Hamiltonian is equal to 0 is conserved. Its time derivative is equal to 0. And in particular, the Hamiltonian is a quantity which is a quantity whose Poisson bracket with itself is equal to 0, and so it follows that the Hamiltonian is conserved. In quantum mechanics, it's the commutator, but same statement. If a quantity commutes with a Hamiltonian, I'm saying it over and over. If a quantity commutes with a Hamiltonian, it's conserved. The Hamiltonian commutes with a Hamiltonian, the Hamiltonian is conserved. What is that Hamiltonian? It's the energy. So this is the principle of energy conservation coming out of, just spontaneously coming out of basic formalism of quantum mechanics. There may or may not be other quantities which commute with a Hamiltonian. If there are, they are also conserved. Let's now come to a particle on a line. Particle moving on a line. Now, what is the connection? Well, first of all, let's just have a particle moving on a line. No potential energy, no forces on the particle for simplicity. Then the particle is described either by a wave function which depends on its position, or the Fourier transform which depends on momentum. Psi star of x times psi of x is the probability to find the particle located somewhere. Psi twiddle of p times psi star twiddle of p is the probability that it has a given momentum. Okay. How do we apply this idea, the Schrodinger equation idea, to the wave function of a particle? Again, the rules are exactly the same. We would like to find some way of thinking about the time derivative of psi of x and t with respect to t. All right, now what we're doing is we're doing the analog of what we did before. Instead of writing a state vector psi of t, I'm just writing the corresponding wave function, psi of x, which also depends on time. Wave functions depend on time. If they didn't depend on time, everything would be frozen. And so for a particle on a line, the state vector can simply be replaced by a wave function which depends on x and t, or its Fourier transform which depends on momentum and also t. How do they evolve with time? They must evolve with time by the same set of rules, minus I times some Hermitian operator, still called the Hamiltonian, acting on psi of x and t. Same set of arguments. And I've simply just removed the brackets here by remembering that functions are vectors. Functions of x are vectors, so I don't need, it would be a little bit redundant for me to put a ket symbol around this, since we remember that functions are a vector space. All right, now what operator? What operators do we have around? Well, we can multiply psi by functions of x. That's something we can do. So just multiplying by some function of x is a linear operator. And we can differentiate psi. We can do all sorts of operations involving multiplying by functions of x, differentiating with respect to x. They're all linear operators. They're all linear operators on these psi of x's here. For example, just multiplying by x, that's the operator that corresponds to position. What about the operator that corresponds to momentum? That's minus I d by dx. Let's put the h bar into this. Minus I h bar d by dx, that's momentum. Okay, what do we know? We know classically. Now, classically is not a different theory. Classical physics is the limit of quantum mechanics for rather heavy objects, which are heavy enough that quantum mechanics is not important for them. But it's a limit of quantum mechanics. It's kind of a special case of quantum mechanics in a certain limit. What do we know classically about the motion of a particle on a line? We know that the energy, which we can also think of as the Hamiltonian classically, but we know that the energy E, which I'll also remind you is the Hamiltonian, is what? It's related to the momentum. It's the square of the momentum divided by twice the mass of the particle. I've simply used kinetic energy as 1/2 m velocity squared, and momentum is m times velocity. Just solve this equation for the velocity, plug it back into here, and the answer is p squared over 2m. That suggests, does not prove. You can never prove something about quantum mechanics from the classical physics. You can suggest, or you can, if you like, say the classical limit has an energy which is p squared over 2m. A suggestion and a guess is that the quantum mechanical Hamiltonian is also p squared over 2m. What does p squared over 2m mean in the quantum mechanical context? Let's guess now. P squared over twice the mass. But now this p is an operator. What does this mean? What is p? P is minus I d by dx. So if it was just p that appeared here, we would just write minus I d by dx, and this would be a differential equation for psi. What does p squared mean? P squared means p times p. When you multiply operators, it simply means you multiply the operator. If you apply it to a wave function, you first apply the first operator, and then you apply the second operator. So here's what p squared means. P squared on psi of x means minus I h bar d by dx being applied to minus I d psi by dx. This is p acting on psi, and here's p acting on the result. That's just p squared on psi. Okay? So now we can write the Schrodinger equation. The Schrodinger equation just becomes that it's minus I, p squared. What's p squared? Minus I times minus I is another minus sign, it looks like to me. Missing an h bar here?
Yeah, it's just h bar squared.
H bar squared, the second derivative of psi with respect to x. That's what this means. d by dx times d psi by dx is just the second derivative of psi with respect to x.
Don't you get I squared there?
Yeah, I squared, it's I squared, which is a minus sign, no more I yet.
And
And you need an H.
But you get a minus
Schrodinger's
one.
equation, don't you?
Is it a minus? Yeah, minus I times minus I is the same as plus I, yeah, minus. Yeah. P squared is minus I times minus I is minus, right?
Yeah,
Yeah, minus.
it's just a minus sign.
Minus. Oh boy, I've lost track now. Wait, so it was a minus I from here, right? Minus I from here,
Right.
and then p squared I think gives me another minus. Yeah. I think I got it right. In fact, I think I had it right in the first place.
You should put an H bar in the Schrodinger's equation as well if you're going to keep it for P.
Where?
And the original Schrodinger's equation doesn't have.
Oh, yeah, there's a minus
Oh,
sign.
good. Yes, you're absolutely right. So I think I'm just going to do it over again. Let's just do it over again. Let's do it over again. Keep all the factors. Okay. So our basic rule is that I h bar d psi by dt is equal to h psi, right? Do I have it right? Is that what I told you in the beginning? Yeah, all right. I h bar times d psi dt. Now, what is h? H is p squared over 2m. And p, each factor of p, 1 over 2m, each factor of p is minus I h bar d by dx. We have two of them. There's another minus I h bar d by dx times psi. So altogether, the right-hand side is 1 over 2m. I have the feeling I've still lost a minus sign. No? No, okay. 1 over 2m, h bar squared, minus I times minus I is minus 1, and d second psi by dx squared.
Right, now you'll get a minus I when you bring the left-hand side over.
That's equal to I h bar d psi by dt. And if I like, I could divide away the h bar here. So we get one h bar on the right-hand side. And then if I like, I can multiply this by minus I, get rid of the I over here, and then I'll get what? Plus I on the side? Plus I on the side. I don't see any particular, well, okay, let's do it. So we get plus I on this side. Okay. That's, this is the Schrodinger equation for a free particle. Right? For a free particle on a line with no forces on it, and we'll come to forces next time, but for a particle on a line with no forces on it, this tells us how the wave function changes with time. The basic principles are exactly the same as for the polarization. The Hamiltonian has to be a Hermitian operator. Incidentally, you might ask, how do I know the Hamiltonian is a Hermitian operator? Well, the square of any Hermitian operator is also Hermitian. That's easy to prove. So p squared is as Hermitian as p itself is, and we'd already proved that p was Hermitian. So p squared over 2m is a Hermitian Hamiltonian. Perfectly good. It does stand for the energy, and this is the Schrodinger equation with all of its h bars and i's in place. Okay. Next time, I think, well, let's see, maybe we can still solve it. Yeah, let's solve it. Let's solve it while we're at it. In particular, let's look for solutions of this equation which are eigenvectors of the momentum operator. In other words, let's look to see how the time dependence works for eigenvectors of the momentum operator. Eigenvectors of the momentum operator are just e to the I p x. P is the eigenvalue. Shall I put the h bars in? I guess I should put the h bars in since I've kept them around. P over h bar x. P is a number. It represents the momentum. It represents the eigenvalue of of the momentum operator. We've done this before, e to the I p over h bar x. Those represent wave functions which have definite momentum. All right? Now, we can do something to this and still have it of the form e to the I p h bar over x. We can multiply it by a number. It's still an eigenvector of momentum. In fact, we can multiply it by a time-dependent number, a function of t. It still is an eigenvector. At every instant of time, it's still an eigenvector of the momentum. When I differentiate with respect to x, this f of t is just a complete spectator. And so when I calculate what the momentum operator does, the f of t is a complete spectator. It does nothing at all. And this is still an eigenvector. At each instant of time, this is an eigenvector of the momentum operator. Why did I put this f of t there? Because without the f of t, there would be no time dependence to it. And I'm looking, and I know that there has to be a time dependence. d psi by dt is going to be whatever this is equal to. So let's see if we can figure out what this f of t is here. All we have to do is apply the Schrodinger equation to it. Let's first calculate the psi. This is psi here, psi of t. No, I don't think there is. I don't think there is. Okay, so let's calculate d psi by dt. When I differentiate with respect to time, only f gets differentiated. So psi dot is equal to f dot times e to the I p over h bar x. That's the left side of the Schrodinger equation. Now let's take the right side of the Schrodinger equation. That's equal to I h bar over 2m. And now the second derivative of psi with respect to x squared. Each time I differentiate with respect to x, the f, of course, that's just a spectator. Nothing happens to it. Just stays there. Now we have to differentiate the e to the I p dot x twice with respect to x. Each time you differentiate, it pulls down an I p over h bar. So that gives us an I p over h bar squared times e to the I p over h bar x. Okay, let's see what we have. Both sides of the equation have e to the I p over h bar x in them. We can cancel that off. Let's cancel that off. The rest of it is just a function for, is just an equation for f. And it says that f dot, the time derivative of f, is just, let's see, there is 2 powers of I here. That's a -1, and another I here. So that's minus I. How many h bars?
1.
In the denominator. So there's a 2m h bar in the denominator. There's a p squared upstairs. And an f. Is that it? Is that right? I think that's all there is. No, I canceled one of the h bars in the denominator with the h bar in the top. There's 2 h bars in the denominator. Because there was 2 p's, so each p came with an h bar. Yeah. I think it's right. Okay, so here we have an equation for f. It says that time derivative of f is a certain number, complex number, times f. What's the solution? An exponential. And here it is. F is equal to e to the minus I p squared over 2m. I'll put the h bar next to the I there, times t. I've discovered what f is, and my whole solution then is e to the I p over h bar x minus I p squared over 2m h bar times t. That's it. That's the solution of the Schrodinger equation corresponding to a momentum eigenstate. Notice that it changes with time. But it changes with time in a very, very simple way. It changes with time with a pure phase. What does that say about the probability? Well, okay, we're now talking about a particular momentum eigenstate. We're not talking about a superposition of momentum eigenstates yet. This is some specific momentum eigenstate. And that's how it varies with time. I think we'll quit here and come back to this next time. We can ask various probability questions. We can ask, for example, does the probability for a given momentum vary with time? Does the probability for a given position vary with time? But we'll deal with that next time. Incidentally, you might want to prove to yourself that the momentum commutes with the Hamiltonian. The momentum p commutes with the Hamiltonian p squared over 2m. That's a little exercise, and that exercise proves that momentum is conserved.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.